So as the title suggests, I will go through why in standard supervised learning settings, why reporting a single probability is not good enough for for uncertainty quantification, or more like confidence related to the prediction. Okay, so the talk structure is like this. So I'll start by motivating why single probability is not enough, and then talk about how second order formalism can help a little bit. And then talk about some ways, some algorithms that allow us to achieve that, and some recent progress in that direction as well. So let's begin by a motivating example. So this is the usual pipeline from prediction to deployment. You collect training data, you learn a model, you kind of verify your model in some carefully constructed test set, and then you deploy it in practice, hopefully. Of course, this will more like be a loop in practice, but the ingredients are usually you have a predefined outcome you want to see, you have some input, and then you want to build a model going from X to Y. So suppose now the model tells me I'm having stage 3 cancer tonight. So it's a very shocking news, but would you trust it just by looking at prediction of this kind of hard labels? So the deployment question is often not only whether the label is correct, but whether the prediction is reliable enough to act on for further decision making. So as you can imagine, just reporting hard labels are often not good enough. So it's probabilistic prediction where you predict a probability as an output, the answer for this. So a probabilistic classifier often outputs a distribution rather than a single label. So it maps X to the, for example, in this talk for simplicity, I'll focus on classification. So going from X to the PMFs over Ys. So here now we see that my predictor says that I'm having stage 3 cancer with probability 0.87. So this is already a major improvement over a hard label. Now at least I have some ways to kind of talk about the confidence of the prediction. But this reported probability is still only a first order statement about Y. So we need to understand what this first order statement is about, or what this probability even mean. So first of all, this probability is used to describe the randomness in the outcome. So condition on X, which is, for example, my health information, what is the stochasticity left after observing X about the measurement of having whatever cancer I have. So this object itself does not describe our ignorance about the probability statement we're given. So first of all, let's try to understand what this first order probabilistic learning is even trying to do. So we often assume there's this data generating process, PXY, the joint. And in most cases, we're happy to say we first sample the descriptors, the X, the covariates, the inputs, and then nature will give, based on the input, then generate a label. It's a bit weird to start with a label and then generate the descriptions, but that's not the key point here. If we use something called strictly proper scoring rule, in this case, just take a log loss, then in machine learning problem, we often do optimization, right? So there's this thing called population risk, which kind of measure so we're trying to learn the function f, and then it kind of compares the quality of f to the actual distribution p of 0 here. So if we now decompose this a little bit, then we can see this log loss can be written as an entropy term that has nothing to do with my prediction. So you can think of it as an inherent hardness of this problem, plus a KL between what I'm trying to predict and the nature. So if I want to minimize this risk, obviously, I want to kill this KL term. So that's why the idealistic probabilistic predictor is actually the ground truth. So this sounds crazy. Why do I need to go all the way and say that the best is to report the ground truth? It's because there are many cases you can use something called just proper scoring rule, and there can be models that are not ground truth, but good enough according to this optimization objective. So we know that it's not surprising that to be a good predictor, you should tell me the ground truth. But ideally, as I said, ideally we want the ground truth, but in many cases, we don't have the ground truth, right? So we often minimize the empirical risk, not the population risk. The true conditional might not even belong to the chosen hypothesis class. So for example, my model complexity is not great enough to capture the very complex conditional distribution. And even if the first two things are solved, there's this problem of optimization. And with non-convex loss landscapes and stuff, it's very difficult to actually get my empirical risk minimizer. Right? So because of all this, the learned probability, the F, let's say F hat we can provide, is only an estimate of the ideal first order probability. And I'm claiming here that this probability, this first order probability is the goal of the learning problem. We want to learn this object. And then what we present what the learned probability from the model is only an estimate of this thing. So just reporting a probability factor doesn't really tells you how confident are you with respect to predicting this factor itself, right? So we still need to express uncertainty about this estimate. So in that case, we also need to recognize that just having one single probability is not enough because it cannot separate something what people call aleatoric and epistemic uncertainty. Even if you don't like putting names, this example is quite obvious. So let's say we have a probability that says that py being true given x is 0.5. So in this case, there's high randomness about let's say we're doing conflict, y is conflict, right? So it's kind of a fair coin, and I really have no information to tell me whether the next draw is going to be head or tail. On the other hand, imagine you have now a hierarchical model, and you have theta 1 and theta 2. They are, to you, both equally plausible, but they tell you very different things. And in this case, some school of thought will argue this has very high ambiguity. But a lot of Bayesian type argument would require you to kind of summarize this distribution and now report py given 1, py equals to 1 given x is 0.5. Then in this case, we go from one case where we have a lot of ignorance, and then we try to report this ignorance by reflecting indifference and say that the probability mass given to 1 and 0 will be equally 0.5. That's the ignorance state. Or there's another case where the randomness actually is 0.5. But in this case, because I report a single probability, I can never tell them apart. So that's kind of one very classical standard way of justifying why single probability is not enough. And I think this Julian used this example a lot before too. So someone else could argue, wow, what about calibration? We all know that just training a neural network and reporting the softmax is not good enough. We have to look at the ECE, the expected calibration error, and sometimes correct for it. And then in that case, calibration then kind of reflect reality. So it's good enough. Why do we need to invent all this crazy machinery for higher order formalism? So first of all, let's recap what calibration means. So a simplest case, let's say a binary probabilistic predictor is calibrated if whenever my model predict this set of images being true with probability C, among those, C% of them actually are true. Right, that's what the very simple calibration means. So in some sense, you can interpret calibration as trying to ask whether the reported probabilities, which by itself can have no meaning at all, no semantics, matches the empirical frequency observed from data. But in many cases, you can show that a good calibration doesn't mean a good predictive performance. Let's make this interactive. Do you know why?
You could always give the average of the entire population as the prediction, then conditioned on this prediction, you are always likely to get the empirical frequency that you report.
Ding, ding, ding. So we have a winner here. So yes, so as Anurag said, if we coarsen our conditioning space by a lot, which means we don't use any information from X at all, then just taking an average over Y is a calibrated predictor, but it's not very performative predictor. And also after that, calibration is still a first order probability, so it inherits all the problems, not all the problems, but the problems we mentioned just now, that is this ability to distinguish between inherent randomness and ignorance of the modular. So on the right-hand side, you will see two examples of calibration. One is like underconfident, and the other one is overconfident. I forgot, but something like that. So the takeaway here is to understand that, well, calibration is very important. It helps us understand what this probability-like numbers really can mean, or the semantic meanings, but themselves still doesn't tell you the uncertainty associated to this probabilistic prediction. So at this point, we can, for example, look at two layers of uncertainty. So we have first order uncertainty. So even if you don't like the name aleatoric, epistemic, which I don't like either, you can call it first order uncertainty. You can have py given x equals x. That describes the randomness in the random variable y once the predictive mechanism, or once you observe the x, which combines the information structure. You can then talk about second order uncertainty, which is related to uncertainty about this probabilistic prediction. And this kind of describes the incomplete knowledge about the predictive distribution itself. So yeah, it's a very simple takeaway. So to distinguish the world is noisy from the model does not know, we need a higher order formalism. So what are some good second order formalism? What should they do, right? So first of all, they should represent more than a single predictive distribution. Otherwise, they just collapse back to first order mechanism. It should preserve information about which alternative predictive distribution remains plausible. It should support downstream decisions. So there should be ways to consume this representation to do something meaningful or useful. So at this point, from this point onwards, the talk is not just focusing about how to learn py given x, but about our uncertainty of py given x when learning about py given x. So that's kind of the motivation. So let's look at some common ways to represent uncertainty about probabilities. So there are two commonly used second order formalism. So if you're still confused by what I meant in the previous slide, so this is a good example. So the first page, I showed you that the model predicts me having cancer. So that's kind of like a hard prediction. There's no probability information. Now the model said I have cancer of 87%. So that's kind of like predicting, putting a stamp on this probability simplex. But when it comes to higher order formalism, you can either look at second order distributions. So you have a distributions over the probabilities that kind of each of them tells you the plausibility of that particular probabilistic model. Or you can treat things more like bounds and sets, and then come up with a set of models that so far you cannot rule out from the given evidence. So that's kind of two common formalism. One is distribution based, one is set based. The semantic meanings are often different as well. So of course, a lot of us are trained in Bayesian statistics. So this is one way to kind of motivate the second order formalism. So Bayesian approach places prior over parameters and update using base rule, right? This is the prior, this is the likelihood, this is the evidence term, and then we have the posterior. Once we have the posterior, it actually very naturally induces a distribution over predictive distributions, right? You can just work on the work with the likelihood. And if you want to predict one thing in the end, then you usually do Bayesian model averaging to get back your first order prediction. And a lot of Bayes decision theory just tells you to focus your analysis on this posterior predictive. So here, even before going here, you see that the second order objective is the posterior induced distribution over predictive distributions. But in practice, there are quite some challenge to kind of popularize large scale Bayesian approaches. So for example, computing this evidence term is extremely non-trivial in practice because when we learn Bayes stuff, we usually say, the prior and the likelihood are conjugated, so we can just compute things analytically very nicely. When it comes to, let's say, Bayesian neural network, that's no longer the case. Your prior likelihood are no longer conjugate, and with very high dimensional stuff, your parameter is simply too high dimensional to actually kind of solve this integral, I would say. Of course, there are many ways to there are many ways to overcome this problem. Like maybe you cannot solve the evidence term, you cannot compute for the evidence term exactly, but you can resort to approximation techniques. So here is one that looks like that's called this objective is called evidence lower bound because it is the lower bound of the evidence term. So if you maximize, so imagine you have elbow and then elbow, which is the evidence lower bound, and then you have the evidence term. If you kind of maximize, try to push the elbow as big as possible, then you will kind of get to the lower bound. Get to the evidence term. So that's kind of the intuition. For those who are interested, if you stare at this term long enough, you kind of see the connection between frequentist and Bayesian from an optimization perspective, where the first term is like an empirical risk minimizer term. If you now set the approximation family are all possible directs, then this is simply solving ERM with a regularization term here. So that's sometimes from an optimization perspective, if you forget about all the statistic stuff, Bayesian or approximate Bayes to me is like a continuous spectrum of ensemble models. That's my understanding. But today's talk is not about this. So yeah, we have this. And yeah, as I said, it resembles a distributional empirical risk minimization plus some distributional regularization term. But of course, there are many attempts to do Bayesian, more than Bayesian machine learning at scale. But perhaps there are other simpler alternatives. And by Vatnik's rule, we don't have to solve a much harder problem if the angle is not that difficult problem. Is that the Vatnik's rule? Something like that. So we don't have to go, let's say, if our goal is to get prediction and some uncertainty, maybe we don't really have to do all the Bayesian stuff just to get an uncertain score. That's kind of an overkill. So that's why people start looking at things called deep ensembles in 2017. It's basically ensembles with deep neural networks. So what you do is you train M neural networks independently. You don't even shuffle your data, not like in bagging and stuff. You just don't care about size. You don't care about dependence. You don't care about anything else. You just train them independently with M initialized parameters. And then for each input X, you can then collect the predictive distributions like this and average them to get your first order prediction. So here's an example. You have X and then boom, boom, boom. You have different networks, boom, boom, boom. You have different outcomes, and then you kind of combine them in some ways. And then you can treat this disagreement among the members as some notion of epistemic uncertainty. But at this point, let me give you one instantiation of this disagreement. So first, you can compute the pseudo, or this is actually the posterior predictive, or just call it the average. And you can look at the entropy of this average prediction, which allows you to kind of decompose it. So the whole idea is kind of like the Bayesian principle kind of suggests us that we should average all the possible models. And if you look at the underlying entropy which is a measure of uncertainty as well, or quantification of uncertainty. If you look at the entropy, you can actually decompose them using very classical results from information theory, and then you can interpret them as average model entropy. So what does my candidate think about the inherent stochastic randomness of this phenomenon that I'm trying to model? So that's what this average member entropy is trying to do. And you can look at the disagreement between all these points or these candidates with the barycenter of the prediction. And that kind of tells you the disagreement. So that's why people in ML will call the first one the aleatoric uncertainty, or I would just call it a number trying to estimate the aleatoric uncertainty. And then this is kind of the quote unquote epistemic uncertainty. So when it comes to deep ensemble, there are people claiming that, hey, deep ensemble is just another approximate Bayesian technique. And they have some justification for that. Basically, they treat ensemble members as sample predictive distributions. So the idea of, I'm not going to show the proof, but the idea, it's not even a proof. The idea is basically, again, to realize that when you solve a Bayes rule, you can write it as something like a average likelihood term plus some regularization between the prior and your posterior. Once you have that, you can treat it, you can think of optimization, frequentist optimization, as trying to draw a sample from this Bayes rule objective. And if you do it multiple times, then it seems like you're drawing from different modes of this variational formulation of Bayes rule. That's not important here. Just know that deep ensemble sometimes or oftentimes are interpreted as an approximate Bayesian solution. And because of that, it's kind of well justified to now look at some Bayesian style uncertainty quantification techniques such as mutual information, label-wise variance, or distance-based approach. So in this distribution-based interpretation, people often ask, so how should probability mass be assigned to candidate predictive distribution, right? And here you can obviously, the answer is put 1 over m to everyone. But I want to offer an alternative in this case. Instead of forcing a Bayesian interpretation, instead of saying these are samples from a hypothetical metaphysical posterior distribution of weights, why don't we just directly treat them as a set of predictors? So we can just read this collection of predictors as a collection of plausible, whatever. We just treat them as a collection of probabilistic predictors. And then it turns this problem into kind of like, how do we aggregate information from probability judges? How can we collect the evidence and this kind of stuff? So you can think of them, as I said, you can think of the ensemble members as probabilistic judges. And the set basically records which predictions remain plausible among all these judges. And we don't really need to put more interpretation than what we did just now by thinking about hypothetical, metaphysical, posterior distribution that we never actually care about. So the probability-based approach will say what candidate model remain plausible with the degree of that. Here we flipped it. We say which candidate predictive distribution should remain admissible now that we have this set of judges that kind of each trying to tell us something. And this gets us into the language or the field of imprecise probability. So a credal set is a closed and convex set of plausible distributions. And from there, we can talk about something like extreme probability assessments to events. Like you can look at this thing called lower probabilities, and this is like the upper probabilities for all the events you care about, and that gives you a very natural notion of bounds. So this is useful when the available information tells us what probability remain plausible, but not how to assign a precise second-order distribution over them. So mathematically, the biggest difference is now it's a set, not a distribution. So how do we apply this kind of imprecise probability perspective to this set of deep ensembles, or this ensemble set? So for a fixed input, the ensemble will tell you different probabilistic judgments. So they are a collection of probability mass functions. And for each of the class K, you can look at the singleton event lower probability defined like this. So let's say this is a cat, and you look at the smallest probability assessment assigned to this class. Then you can form this probability interval credal sets, or some other group, they call it the box credal sets. I don't know why it's a box, but interval probability, probability interval credal set, which is the set of PMFs that do not violate these bounds given by the judges. So they're like a good enough distribution because I'm not violating the evidence so far. And this same ensemble can support a distribution-based representation or a credal representation, right? Because for this set, you can just put 1 over m to each of the model. Now you go to the Bayesian perspective, or why don't you just treat them as bounds and then you have the credal set. Obviously, there are merits to both, which I will also talk about later on, about some recent comparative study we have done between these two methods. But here's official visualization. So one is, again, distribution. The other one is sets. So the same raw ensemble predictions can be interpreted either as a discrete second-order distribution or as a set of plausible models. And in that case, let us show you what people call almost like the simplest you can think of in precise probability idea applied to deep ensemble. So here you get multiple sample distributions. So they call it sample, but you can just train a different way. Just give me a set of probabilistic judgments. Then you can extract the upper and lower bound, like we said, and that gives you the credal set. And then you can do some kind of uncertainty quantification techniques from this credal set, get a number, and say that that's my confidence associated to my prediction. But of course, someone will ask them, what is the prediction itself? There are many ways to generate a probabilistic prediction from a collection of sets. Then for those, you can study for example, some of the geometry of this set and stuff. There are many ways to justify, and it's not only just taking the arithmetic average. So this is what Kai Jiang, my current postdoc, when he was doing his PhD with Fabio Cozzolin, came up with, called credal wrappers. For some reason, he called it a spotlight in ICLR. So a credal wrapper converts any collection and then into a probability info set, and the set makes a set-based interpretation available without changing the underlying predictor. I think the most likely reason why that work received some good feedback or at least good acceptance is because by such a simple change of semantics, you can already observe quite statistically significant, more than statistically significant improvement in some of the downstream decision tasks. So this is an application of this credal on credal wrapper. So basically what he did, I think, is you have deep ensemble. You can either go to the root of Bayesian perspective and do mutual information and stuff, or you can take the root of imprecise probability, just treat them as judges and look at a set of compilable distributions. And then you use it for some decision making called OOD detection. I'll talk more about it later. But just for now, just think of it as the usual ML metric. And then you see that the prediction, the collection of stuff inside is the same. The set is still the same set of predictors, but with just a different interpretation leading to different kind of operation downwards. You see the improvement is quite significant in ML metric perspective. No? So yeah, so this is one piece of empirical evidence that maybe in precise probabilistic perspective can bring in some interesting things to machine learning. And it doesn't sacrifice scalability, because if you do deep ensemble, you do deep ensemble. What changes afterwards, what math you use to kind of do the post-processing. But what we've seen so far, this deep ensemble is simply randomly training different neural networks, right? What's that time? You're just randomly training different neural networks. So yeah, so this part of the talk is based on our ICML paper this year at ICML. Yes. So what most ensemble to credal methods still inherent. So before, like the credal wrapper thing was quite early, there are already a few more sophisticated attempts to kind of improve it or blah, blah, blah. But then they are still trained with the same set of data and essentially the same objective in mind. So they're still solving the empirical risk minimization problem. So in this case, it's very natural and even important to ask ourselves, where does all this disagreement come from, right? Because we know as n goes to infinity, there will be no disagreement anymore. And it makes sense. I hear to what people think epistemic uncertainty should go away. We have infinite information. But we never really arrive at infinity, right? Even in statistics, people care more about finite sample analysis than asymptotics nowadays. So we should then ask, well, at this time slot of time, what does this disagreement really mean? So I would say in the most classical deep ensemble, we can think of it as kind of the sensitivity of the loss landscape or optimization to different initialization. There are also perhaps there can also be the difference between different local minima, or there are people who use different architecture and then look at how it's sensitive to this architecture. But these are not, in my opinion, maybe not the best variability we want to look for when we want to be kind of safe and make trustworthy type of prediction. So here, the idea is if all ensemble members solve the same problem, the disagreement may be informative, but not necessarily tied to different deployments, but it is not deliberately tied to different deployment assumptions. So what I mean by this deployment assumption, I will explain in 2 slides. So kind of the motivation of that work is to say, instead of hoping random training gives you meaningful diversity, why don't we train members to answer different but meaningful objective in this supervised learning problem? So instead of ensemble, you use different seeds, but same objective. Here, we actually change the objective. So it's not only just empirical risk minimization, but perhaps we add a different flavor to it. And the way to do it is, here the idea is it's not just to diversify for diversifying, but trying to have some more meaningful disagreement that corresponds to distinct, plausible views of this learning problem. So the way to do it is to actually use a distributional shift out of all these stuff. So basically, empirical risk minimization implicitly assumes that the error that I observed during my training is a good enough proxy to the error I observe at deployment, because they are both trying to approximate the population risk. But in deployment, we often believe that p-test will be somewhere close enough to p-train, right? I think we are no longer just saying that p-test equals to p-train, but we are allowing some kind of perturbation. There are many reasons for that. There could be distribution shift, covariance shift, confounding shift, or just this performative effect and stuff. So there are many reasons why at test time we will not be seeing what we have seen so far. So this idea is captured nicely under the field of distributionally robust optimization, which instead of just solving an ERM-like problem, we allow ourselves to choose the worst case, the distribution that gives us the worst loss. So we are very pessimistic, then train with respect to that. And if we make a small assumption that p-test is inside the ambiguity set, so it might sound very restrictive, but it's actually a relaxation of saying p-train equals to p-test. Then we have some kind of a performance guarantee. So DRO makes uncertainty applied to the deployment part of the training objective rather than only part of the post-hoc uncertainty score. What does this mean? Yes, as you can guess, some part of these slides were generated using language models. These takeaways are that. Anyway, so we use this idea in mind, and we come up with an approach called credal, or someone started calling him credal for some reason. So credal does the following. So we want to train an ensemble member under different robustness levels. So each of them will see a different perspective of ambiguity or this oddness. So member M will solve a CFAR type objective. So NRAC is very familiar with CFAR, which can be written as a collection of weights that weights the loss function. And a smaller delta M gives a more conservative member, and delta M equals to 1 recovers the standard ERM. So the maps is not that important here. Just understand there are different ways we are relaxing the objective. So technically, you don't have to use CFAR. You can use other ways of setting up the DRO problem. It doesn't really change the semantic meaning of this work. And then the resulting ensemble predictors are converted into a credal set by this class-wide bounds. The reason why we use CFAR in this case is because there are very nice analytical, not analytical, but the optimization is super easy. What you do is you first compute the loss of these points, you sort it, and then you cut it after a certain threshold. And then just compute the loss, average loss, and then backprop. So here is an overview. So you have input, you train different networks under different robustness assumption, and then you do things. You have a set of prediction, and then you do kind of like a convex, not convex thing. You do the box credal set. So when we evaluate this approach, one thing we need to be very honest about is this kind of epistemic uncertainty level of prediction, or like finding the uncertainty score or the confidence score accompanying my prediction, probabilistic prediction. There's no ground truth to that. It is more of an unsupervised learning than a supervised learning, because what is the ground truth uncertainty of my prediction? Like what should be ground truth But if there's any ground truth, or if there's any desirable epistemic uncertainty, then it should be zero, right? So there's really no ground truth, and we cannot just look at some laws, or in a lot of our submissions, we keep seeing people asking us for ground truth, epistemic uncertainty, ground truth, Shapley values. That's like crazy people. Yeah, but yeah, anyway. So here we have OD detection problem. So what it is really is we see a bunch of, let's say, X-ray images. We train an algorithm, but at test time, someone throws us a hand X-ray image. It is definitely not what we have seen so far, and we want to be able to detect this departure. One way to do that is to turn it into a binary classification problem and say that, well, this image is OD if and only if some ways to measure the uncertainty of it is greater than a threshold that we have chosen from, let's say, some validation sets. So therefore, as I said, OD detection is to treat it as a binary classification problem using the estimated epistemic uncertainty. I don't know whether estimated epistemic uncertainty is the right word. Maybe just epistemic uncertainty. And because if you say estimated, then it kind of means there is some ground truth epistemic uncertainty. So this is not good. And so the goal is to detect inputs on which the model knows it does not know. So one particular simple epistemic uncertainty quantification method is called the entropy imprecision, which basically looks at the credal set you have and then find the largest disagreement in terms of the first order uncertainty quantification, which is the entropy. This method is not good, but it's easy to compute. And there are more advanced stuff to do this nowadays, including one of our work with Crickmore last year on integral imprecise probability metrics. So here are some favorite figures that ML people love, or at least the reviewers love. Just look at this weirdly colored bar is the top. That's it. We're good. But basically, there are a bunch of different competitors, and we do better. Yay! And but most importantly is what these results tell us is that, at least empirically, disagreement appears more informative when it arises from meaningful differences in training objectives rather than only from random seeds of the model. So that's kind of the takeaway. Okay, so that's kind of, we have 15 minutes left, I guess. Oh, no, right? We have, okay, 5, 10, 10, 10. Okay. Yes. So we also want to show this recent work to you guys. And this is, the paper is not called Elephant in the Room, but more like when you're hearing all this second order stuff, right? The first question you have in mind is which one is better, right? Or like, at least, can we compare them? Like, why do I do this, not that? And the answer is depends on where you're from. I mean, your training, what do you like or not. But and a lot of times, when people do like a credal-based paper, they cannot compare Bayesian neural network. Not because they don't know about the other side of things. Mainly, okay, maybe Bayesian people really don't know much about IP stuff, but the main reason why they don't compare with each other is it's not comparable. There are many reasons I will explain. But in this work, we're trying to find one particular use case, one particular setting that they are both comparable. And then we try to do some kind of comparative study and see if we can have one conclusive suggestion. We want to see if credal beats Bayesian stuff or Bayesian stuff beats credal stuff, or of course, to be determined. That's the third option. So this part of the talk is based on Kai Jiang's recent work accepted at UAI called Set-Based versus Distribution-Based Representation of Epistemic Uncertainty, a comparative study. So yeah, if someone is in UAI next week or the week after, we can chat. So we have already seen two ways to represent uncertainty about a predictive distribution. We have distribution-based, like this, or we have set-based, like this, which is quote-unquote better. So whenever we talk about better, we need to define the comparison metric, right? So we'll see. But first of all, we need to understand why this question is inherently difficult to answer directly. So suppose we compare a Bayesian neural network with a credal wrapper or whatever. There are many things that are different between them, right? For people, we've done some causal inference, right? We want to compare stuff. You need to fix everything that is fixed, and then just change one little thing at one time. But in this case, it's very difficult because once you use the BNN and then not through a, let's say, a credal wrapper, then perhaps your learning algorithm changes. Your hypothesis space is different. Your architecture will be different. The way you optimize is different. The predictive accuracy of your judges, remember we have this set of judges, they might be different. Putting this distributional-based semantics or set-based semantics gives you different representation afterwards. And then finally, the uncertainty measure you use to kind of convert this representation to a scalar number can be different. So all these things are not the same. Then it makes comparison between a Bayesian neural network with a credal wrapper not very principled. Of course, you can just compute them and use it in OOD detection, but because of all these underlying nitty-gritties, what you get in the end is not really, I would say, trustworthy, or it's not a complete story. So in general, we can kind of put all this under this idea of the prediction will be different, the representation are different, the measure are different, under these three tabs. And perhaps a comparison is only meaningful if these factors are disentangled at best. So how do we do that? We need to construct a like-for-like construction. So a control comparison means we have so the first thing we can control is the set of judges. We can start exactly from the same finite prediction set. And then from there, we can put a distribution-based perspective on it, or a credal set-based perspective on it, which means we can now train a Bayesian neural network, and then we can samples and parameters from it, and then use that to form our prediction set. And then because of Monte Carlo type argument, what you're really seeing is a distribution that has 1 over m on all the points. On the other hand, you can do credal stuff. Or you can simply train a deep ensemble and then put 1 over m on each of them, and then enters the Bayesian perspective, or do a credal perspective. So if we do that, then we have the same neural network backbone that generates the same set of predictions and same average point prediction, right? They're the same points. Only the second order representation in this case is different. So here's a nice illustration. So we have input, we have trained using the same neural network. I don't care how we get there. We can either do deep ensemble type stuff, we get a set, or we do Bayesian stuff, we get also, and then sample, we also get a set. After that, we ask ourselves how to represent the epistemic uncertainty. We can either do this second order perspective, putting 1 over n plausibility of each of them, or we do a credal set. After that, we can also ask, remember, as I said, the measure also matters, right? So these are some commonly used ways to quantify epistemic uncertainty. Mixture information everyone knows. This one is from Yusuf's work 2 years ago. I think this is also from him. Entropy difference is from ancient time, I guess. This one is also ancient time. This one is from our recent work. And then there are 2 downstream work. One is on OOD detection, as explained before. You have chest ray images. Now you put a chicken leg image to it, how to detect that. Or you have selective prediction, which is kind of like you do prediction, you then use the uncertainty, the confidence score to kind of rank the prediction, and then do some kind of selection afterwards. So our study really tries to isolate the representation step before asking how uncertainty score behave in downstream tasks. So as you see, everything only matters from this part onwards. This kind of, how do we get to the set of judges? We don't care. And here is also a very common perspective that people in this field often try to communicate through, which is representation alone doesn't give you an uncertainty score, right? Just having a probability doesn't mean it quantifies your uncertainty. You need to turn them into a number in order to quantify it into a number. That's one perspective. There are counter arguments to that. So here we have predict sample and then the representation, and then we look at the score and we use the score for some decision. So just asking whether distribution versus set is actually not complete. The measure used to interrogate the representation also matters. So it's like, so that is also kind of why this comparison between set and distribution from an empirical perspective is also not easy, because all these things might give different results. So we have two downstream tasks, as explained, OOD, we know. For selective prediction, we first rank so now we have a set of images we need to predict, and we know the ground truth of them. We rank the test samples by the estimated uncertainty or the confidence, and then we reject the most uncertain samples. And then good uncertainty score should improve the accuracy on the retained samples. And then we do that by kind of swiping over the rejection percentage across. And if we do that, we should expect to see a concave curve increasing. But given time, we don't have time. We don't have enough time to go through the details. But just trust me, as two ways to two very common downstream decision that consumes epistemic uncertainty numbers. So in our experiments, we look at different types of predictive models in order to give a relatively broad perspective. We are not a huge lab. We don't have that many GPUs, so we cannot just spam stuff. But the results from here are also already quite conclusive. So we have predictive models like this, and then we have different benchmarks, different data sets. So we have 6 models, 6 uncertainty measure, 14 benchmark, and 10 independent runs. Good enough as an empirical study, in my opinion. So here are some insights we get. So we basically so how do we read this table? So this is saying that the backbone is deep ensemble, or this one says that the backbone is stochastic variation inference, a way to get the judges. This MI is mission information, and this box is lightened up because MI is statistically significantly better than entropy and precision when it is doing selective prediction. So we're doing comparison studies, so we should have p-values and stuff. So they are statistically significantly better. Here we can see that because of this, we can now, because of our control setup, it's quite meaningful to compare across methods. So mutual information now can compare with, or more like MMI, which is a credal-based uncertainty quantification method, can be compared to, let's say, mutual information, and we beat them consistently. MMI is better than mutual information, mutual information, mutual information, mutual information, mutual information. So you can read all these numbers. I will not bother you with this. So let me summarize all this into findings and takeaways. So the question, the distribution or set itself is not enough, has no unconditional answer. We need to talk about how do we extract the information from this distribution or set. So the ranking changes with the uncertainty score. It also changes with the data sets, the model, the task we're doing. Therefore, claims about second order representation should always state the full evaluation pipeline, especially as there are no ground truth second order distribution. There is one counter argument to that. If you think of it purely from Bayesian perspective, you can say, against with infinity, we can look at the inverse of the Fisher information matrix. That's your ground truth. But that's another story. So yeah, representation plus measure plus task plus data is important to kind of answer this question, at least empirically. Finding 2 is the OD detection is sharper way to see things. I don't like this slide, so let's ignore it. Finding number 3 is that the metric choice matters as much as the representation. So for example, when you do distribution stuff, Wasserstein distance is consistently strong. It captures geometric dispersion of predicted distribution in the simplex, and then the other 2 are not that good. On the credal side, generalized Hartley, which is the most computationally inefficient way to do it, is kind of pays off because it's harder to compute, so maybe it captures more. And the entropy difference sucks. That's kind of like everyone in the field already know this, but they're still using it. So better representation will still need better uncertainty measures. So these 2 concepts cannot be separated empirically. So what does all this really suggest for future work, which is, at first we now, with this set of examples, we already can say that there's no one method completely dominates the other. And therefore we should still researching in both directions. And also I guess this is a summary slide for the whole work. So do not stop at calibration. It doesn't tell you confidence. It just tells you whether it reports whether you have semantic meanings. And when we do all these second order research, we should make the second order objective very explicit. Is it a distribution for prediction or a set of predictions? And if we were to apply this kind of ensemble-based technique in practice, we should ask ourselves, where does this disagreement come in the very first place? And finally, don't just ask distribution of sets. You need to kind of put them in a whole decision-making pipeline. So there are different choices that you need to make, and you can only compare them meaningfully after you have specified all of them. Yeah. So I hope if there's any final takeaway, then just remember one probability is not enough. We need higher order formalism to kind of communicate the uncertainty or confidence related to this probability estimation. Yeah. So that's everything. Thank you.
Thank you, Aaron.